Welcome back. We were looking at what happens when the reflected wave overlaps with or interferes with the incident wave, which is coming at it. It's incident at the reflection, or incident on the reflected wave. So this is the incident wave, this is a reflected wave. They overlap when they meet in the middle, and they interfere. Let's draw that interference in this third spot. Now I want to be really good with my drawing at this point. So here's the here's the reflected wave. Let me try again. And I'm going to move it forward in just a moment. And then I'm going to take the exact same picture. And here, and I'll make this one blue. Or maybe I'll use green. So they overlap perfectly, and at some moments when they overlap, there's constructive interference, and you get a giant standing wave. The standing wave becomes huge. And then, when a little time passes, they overlap, and they cancel out, and the standing wave becomes a flat line. And then a little more time passes, they overlap, and it's a giant wave the standing wave makes. The standing wave gets huge again, and then they overlap more, and they cancel out, and so the standing wave is flat. And then here, after a little time, they add together, and the standing wave is huge. But let's just draw it maybe like this, right? The interference. And so that interference gives a standing wave, but only at certain frequencies, which is probably a shock. We're going to look at that, just not in this video. So why are these called standing waves? Why are they? I mean, after all, they're made from traveling waves. Well, here's the reason. These are called standing waves because the crests and troughs, or as the case may be, rarefactions, let's say compressions and rarefactions, don't move forward through the medium. The crests and troughs, rarefactions, crests, troughs stay at the same spot, or are always produced at the same location in the medium. Let's make this reasonably sized. There it is. The crests and troughs, or compressions and rarefactions, don't move forward through the medium. They always are produced at the same location. But then what is wave speed for a standing wave? I mean, if the crests and troughs have a speed of 0, what is the wave speed? C. Remember, wave speed is c? I mean, in fact, remember how you have, like, the equation c equals f lambda? Right? So if you take the frequency of a standing wave, standing waves have some frequency, the standing wave frequency, and you multiply the standing wave frequency by the standing wave wavelength, standing wave wavelength, you might expect to get the standing wave speed. But no, that's not true. The standing wave doesn't move. The speed is 0. So what is this then? When you multiply the standing wave frequency times the standing wave lambda, what is c? It's just the wave speed. It's the speed of the traveling waves through the medium. The standing wave frequency times the standing wave wavelength gives you the traveling wave speed. In fact, the standing wave frequency is the same as the traveling wave frequency. The traveling wave. The standing and traveling wave frequencies are the same, and the traveling and standing wave lambdas are the same. So lambda is not specific just to the standing wave, it's the same value for the traveling wave. And frequency is not specific to the standing wave, it's the same for the traveling wave. Nodes and antinodes. We already looked at these. Let's draw a standing wave, and we'll make this one a little longer. Here's what I'll do. Like that. Right? Connect this. And after a little time passes, the standing wave is like this. A nice smooth curve, and after a little more time, the standing wave looks like this. Yeah, good. A little more time passes, and it looks like this. A little more time passes, and what's another color? Red. It looks like this. A mirror image of the black line. That's pretty close. That's okay, decent. Right here, no matter what shape the standing wave has, no matter what moment of time we are in, there are dots that I'm marking where the standing wave is never, where the particle never goes up or down. On the string, this spot right here never moves up or down. And here's another spot where the string particle doesn't ever go up or down. And here's another spot where the string is never going up or down. That particle just stays at the same spot, at the center position, the equilibrium spot. Those locations are nodes. So we've drawn 4 nodes in this picture. Node. You must node this term. This is an important term to node. Write this down in your nodes. And other puns. Okay. And then there are other locations that always get to the highest point. Right here. That's a spot on the string called an antinode because it always gets to the maximum displacement. That's the highest that the standing wave ever gets. And here's another spot on the string, another antinode, another particle that is going really far down and then subsequently going really far up. It reaches the maximum displacement of all particles. That's another antinode. Antinode, antinode. And then here's another antinode. Maybe we should mark X's for the antinodes to distinguish them from the nodes. X for antinode. By the way, I'm using AN for antinode. Whoops. AN for antinode because A is amplitude. So don't use A. Use AN. Antinode. There are no uncle nodes. Yuck, 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 yuck. Okay. So nodes are positions where particles always experience zero displacement. This part of the string, this particle, doesn't ever go up or down. No antinodes are positions on the string where particles undergo the largest displacement. So that's this one right here. This part on the string is going really down and then really far up. Particles at the antinodes form the peaks and troughs. And like we saw before, nodes are the locations where there is occasionally complete, perfect destructive interference. Antinodes are the locations where there's occasionally perfect or complete constructive interference. So as the last thing that we do, we're going to check and see whether the statements we wrote down are actually true for nodes and antinodes. Here is the location on a string. Remember, the red line represents like a piece of string that's, like shaking up and down. So here, supposedly, is an antinode, and here is a node. And again, here's an antinode, and here is a node. And it continues. So let's watch the simulation in slow motion and see whether the things we wrote down are true. Select. Okay. Here we go. Now, before I play the simulation again, remember that the red thing here is a piece of string. And so you could, like, imagine breaking that string into lots of little slivers. Here's a little sliver, here's a little sliver of the string, here's a little sliver. And we're going to talk about the little pieces of string, the slivers of string, and what they're doing. So watch. I'm going to put my cursor on a sliver of string moving up and down. This sliver of string always gets to the highest and lowest points on the standing wave. this sliver of string always reaches maximum displacement. That one little sliver. Right? So yes, in fact, antinodes, there are these locations on the string where the pieces of string, the particles, always get to the maximum displacement. Here's another such piece of string that always gets to the highest and lowest points. And how many pieces? There's a third, a fourth, a fifth, a sixth, a seventh right here, and an eighth. 8 antinodes on this standing wave. But there are other locations, like right here. This little sliver, if you imagine a tiny little red sliver right here, that red sliver never goes up or down. That part of the string always stays at the same spot. So that particle is located at a node where there's always zero displacement. Not moving up, not moving down, the displacement is zero. Okay, and the final thing to check again, are the antinodes really the locations where perfect constructive interference occurs? Are the nodes really spots where there's perfect destructive interference? Let's watch. Okay, where do the waves overlap? Let's wait. When do we see two crests perfectly overlapping? Right there. See how right here we have two crests perfectly overlapping, which means the tippy top of one overlaps with the tippy top of the other. And yes, that tippy top overlap occurs at the antinode. And this tippy top overlap, or well, bottom, what's the equivalent? Bitty bottom? No, that doesn't make any sense. The bottoms overlap here at this antinode. The two tops overlap at this antinode. The two bottoms overlap perfectly at this antinode. So yes, antinodes are the places where eventually the two crests perfectly overlap and the two bottoms perfectly overlap. Perfect constructive interference. Okay, now if I let the simulation run and I let a little time pass, then the blue wave travels to the right, the green wave travels to the left, and after a little time, blue's crest will be overlapping with green's trough, right? That overlap supposedly occurs at the node. That's where we have perfect destructive interference, canceling out of the tippy top of one wave and the very bottom of the other wave. So let's see. Let's go ahead in time. Let's let some time pass. And stop right here. Right here. Ah, I'm close, aren't I? Let me try and see if I can move the cursor exactly to where I want it. Let's see. Let me move forward and find a spot where this happens. Let's go a little farther, and right now. Yes. Right now, blue's, the very top of blue's crest overlaps with the very bottom of green's trough. That perfect destructive interference between the very top and the very bottom, perfect destructive, occurs at the node. And it occurs at this node too. And it occurs at this, which would also be a node. Right? So every time the tippy top and the tippy top overlap, that occurs at an antinode. Every time the tippy top and the very bottom overlap, that will always occur at a node. Antinodes overlapping, two tippy tops overlap at the antinode, two very bottoms overlap at the antinode, and at the node, we have, well, kind of see, the top of one and the very bottom of the other overlap at the nodes. So that's true of what we said as well. So yes, this is what our notes have said. On occasion, the two tops of the traveling waves, on occasion, those two tops of the traveling waves overlap perfectly. And where does that tippy top overlap occur? At an antinode. And occasionally, the very top of one wave overlaps with the very bottom of the other wave, of the other traveling wave. Where does that tippy top and very bottom overlap occur? At the node. And that's what these notes say.